Welcome to Brain Vision.
In this question, this is the setup that we have. We have a block of mass M, big M, lying on the table itself, and on top of it is a spring that's attached to another mass, small m. Alright, and what we want to find is the mass of m such that when the small m is actually compressed by a force of 3 mg, the spring actually is able to lift the big M just off the table. Now what does this mean? Right, so it's a bit confusing, so let me break it down for you. So when you compress the small m, now this is the compressed state. And afterwards, when you release it, the small m will shoot upwards and it will extend the spring. Now at this extension, right, there will be some force that's acting on the large m, right, due to the extension of the spring. Right, when the spring is extended, you exert a force, and this upward force would cause our big M to get lifted off the table. So we want the greatest possible value for our M such that it will just lift off the table. So that is when the force exerted by the spring is just enough to overcome the weight of our big M. And what is this force? This force is given as K times the extension, which I shall call D. Now what is D? D will depend on what is the original position, right, or equilibrium position of the spring. So say if this position is the equilibrium position, then D will be this distance over here, D. So at this point, we're going to write down the equations that govern the conservation of energy. So this, I'm going to use this as our initial state, and this is our final state. The total energy in the initial state will just be half kx squared due to the compression. And it's half times k times 4 mg over k squared. This is our initial energy, which is just fully elastic. Our final energy state would be the increase in gravitational potential energy, right? We have mg times the height of 4 mg over k plus d, as well as the additional elastic potential energy that was gained from the extension of d, so plus half k d squared. And now we need to equate this both together by conservation of energy. So this is the initial energy, equate that to the final energy. It's given as 4 m squared g squared over k plus mgd plus half kd squared. So putting all the terms with only m squared g squared over k to the left, so this is actually 8. So we can have 4 m squared g squared over k goes to mgd plus half kd squared. And now to actually solve for our D. Right, so we have minus 4mg over k. So over here, this is a quadratic equation. A is equals to half k, b equals to mg, c equals to negative 4m squared g squared over k. So d is equals to negative b, which is negative mg, plus minus square root of b squared minus 4ac. divided by 2a, which is just k. Now, because d has to be a positive value, right? So we will have to ignore the negative values, right? So we can ignore the negative part, so it's just positive. Inside the square roots, we can simplify this to just 2k, and the k will cancel out, so we don't have any k's. So this is just 2 times 4m squared g squared, which is 8. Add with our our first term over here, we get a total of 9 m squared g squared, which if you take the square root, it's just 3 mg. So it's negative mg plus 3 mg divided by k. So this is actually 2 mg over k. Now we can substitute this into our initial equation given over here. We want our mg, big mg, equals to kd. So this k times 2 mg over k, which is equals to 2 mg, and therefore our maximum m can only be 2m.